My research is related to electronic device development using printing method, a type of additive manufacturing called printed electronics. The device fabricated this way is small and flexible. We print the devices on flexible substrates to make wearable devices, printed sensors, and miniaturized antennas. These devices can also conformally adapt to the surface or contour of a curved host, saving space and weight. We're interested in 2D printing because we're printing circuit. We're not printing object. So it's really layer by layer fabrication of circuit on a surface. And with 3D printing, you have an object that you can have a micro scale height. That's the basic difference. Even though that we can print on, some contours, right? On the 3D, we can print on 3D object, but the printing itself is still very thin layer. That's why we call it 2D. I have one example in my hand. As you can see, the circuit is printed on a Kapton tape with the surface mount processors. And these are 4 biosensors and with its own analog circuits. And you can see how small the device is, and we can easily band that devices. This type of technology can be also used to print on non-planar surface. I'm holding a ping pong ball in my hand, and you can see the same circuit is actually printed on top of a ping pong ball. That shows the potential of this technology that can be used in, for example, antenna arrays printed on the Zhong or nose, or the array of thermocouples on an engine surface that gives you a better detection density and resolution.
I'm involved in one of DOE's microelectronics funded projects, and it's called Threadwork. And it's an exciting project because oftentimes when you look at the full scheme of design, you can start at the materials level in the microelectronics, what materials you're using. You can also start, next up is the materials used in terms of devices. Those devices, which may be looking at processing units, looking at memory, so it's different devices, are used to compose computer systems. With the computer systems, you have different software that's used to manage the computer system, such as your operating system that manages the resources. You have also a runtime system while an application is running that's efficiently utilizing different aspects about your application to interact with the operating system. You also have the compiler, where based upon the language, you're taking this high-level language like a C++ and converting it down into something that's readable by the machine. You can have the programming environment, and then you have the application. So you have all of these different levels when you start to look at going from materials to the applications where you're looking at microelectronics. What we're doing with Threadwork is looking at this co-design. And that is, instead of looking at just that interface between the different adjacent levels, like materials to devices or devices to compute systems, we're looking at connections that may go, for example, from the application to the materials. And it's exciting because it provides an opportunity for some breakthroughs that come from when you look at how is this material impacting all the way up to the application. And so the applications we're looking at are high energy physics, nuclear physics detectors that are being designed for 10 years out, where you're looking at a large increase in the amount of data that's generated from those detectors. And what does that mean in terms of the timing? That for the sensors with the detectors, you want to be able to do some real-time analysis. What are the algorithms that are being used? Then when you take that and you start to say, okay, what are the materials that will be used for the devices? What's going to be the impact in terms of the size of those devices? And now look at it as impacting those detectors. What becomes the size requirements with future detectors? How much power is being actually provided with those detectors? How much power is required if I use this type of material? So we're doing this design in a co-design way where applications are talking with materials. So it's at different levels, but they are looking at those different levels and not just having to go between levels. You're looking at the interactions of point to point, between the levels. That becomes really exciting.